Okay, the last topic in physical chemistry is statistical mechanics. So we've been through a semester of quantum mechanics, we've been through almost a whole semester of thermodynamics, and statistical mechanics is what links the two topics together, links the two courses together, right? What it's trying to do is, hey, we spent a whole semester of thermo talking about energies of bulk stuff, energies of samples, energies of gases, of solids, and their equilibrium properties, without ever actually considering what each individual molecule or particle does. Quantum mechanics is all about, okay, for one particle in certain situations, what does its energy level diagram look like? What are the individual energies of one single particle? So there must be some connection between what we see in the bulk and what we can measure for the whole sample and what each individual molecule has in terms of its own quantum numbers and quantum energies. Okay? So it's all about thinking about all those particle motions we talked about last semester. Okay? Particle motions and interactions, all right? Each individual particle has a certain, what I'm going to call like a quantum mechanical energy, right? And eventually we're going to call these E sub n to remind us that they're quantized, right? Each and every particle has a quantum energy for each motion. Each motion has a separate quantum number. So a single particle has a bunch of different quantum numbers, a bunch of different quantum mechanical energies, and then those contribute to the energy of the whole sample. So what we imagine is, in a perfect world, we could take a box, we can put a whole bunch of molecules in there. Maybe they're just atoms, maybe they're just particles. And we could take each one by one and say, okay, for this guy in the corner, how does it move? What are its interactions? What does the Hamiltonian look like to account for all those motions, all those interactions? What are the set of quantum numbers that it has? Okay, because it might be a different set of quantum numbers than this guy here. That'll give me an idea of what the energies are. And then if I consider all the different quantum numbers of every single guy in this box, I'll know every single little energy, and I'll be able to talk about our U. I'll be able to talk about our internal energy as an average of all these energies. Okay? This ends up being impossible. It's the ideal case, not like in an ideal gas or ideal solution setting, but it's like if we could do it, it would be great, but we can't. But we can use statistics. And what we can talk about to infer what the distribution of energies might be inside this box is we can talk about averages, we can talk about probabilities, we could talk about likelihoods. We can look at distributions, and then instead of having to know every little bit of information, we can talk about, okay, on average, what do the quantum energies look like? And then how does that affect what you observe in the bulk? So that's how the connection is made. We understand there are quantum mechanical energies, quantized values, quantum numbers that can be related to the bulk, but there's also a distribution of molecule energies that we have to consider that allow us to make the connection between the two realms of physical chemistry that we've discussed so far. So this impossible task becomes possible when, instead of saying, I need to know everything, I just need to know, on average, probably the likelihood of populations existing inside here with certain quantum number sets. Okay? And I'm going to try to make that statement over and over again and try to reinforce it because it's the central theme behind statistical mechanics. It's why that word statistical is there. Because we don't need to know everything. But if we know in an average way what's happening, that'll still give us information about the bulk. Right? So we're not going to be able to do a ton of derivations here, so you're going to have to take my word for a lot of the equations that we use. All right? But what we do to kind of think about developing averages, developing probabilities, is we talk about ensembles. Okay, we talk about ensembles. Now, the ensembles that we're going to talk about this semester are canonical, which means that we're just taking a certain set of experimental values and we're saying that they are constant. So what a canonical ensemble says is we're going to be looking at chemical systems that have a fixed N, a fixed V, and a fixed T. We're going to be looking at chemical systems that have a fixed number of particles, a fixed volume, and a fixed temperature. Okay? Now, temperature becomes one of the main focuses on StatMech because temperature provides motion. Temperature provides a thermal energy, right? And that'll really help us when we start to talk about distributions and so on and so forth, all right? Before we get there, what is an ensemble, right? The easiest thing to do is to go ahead and look at, and again, we're kind of missing out on a lot of derivations, but you can look at figure 17.1 in your book, and that's on page 695. And essentially what an ensemble is if we want to get an idea of what's happening on average, we're not just going to look at one system, right? We're going to look at a bunch of systems. All right. And I could keep filling this with dots. And the reason it's inside a bigger box is because we're going to say that this bigger box is insulated. And then we're going to call this like system 1, this system 2, system 3. Each one of these different systems comprises our ensemble. So our ensemble is all these different systems. Now, each and every system has the same N, V, and T. So here's how we develop statistics. Here's how we develop averages. We set each and every system up with the same number of particles, say like a mole of particles. And each system has 1 liter of volume. And it's in this thermally regulated environment where each system has 25 degrees Celsius of temperature, okay? And then we look and we try to observe similarities that show up with all your different systems. Think about them as each and every one of these is a different box that has a mole of particles. They're not going to behave identically, but they will give us a way to figure out how they behave on average. So our ensemble, we might look in this box and we might see an energy that we're going to call like energy 1. And I might look at this box and, oh, well, it was really interesting. We actually get the same energy. I'm going to call that energy 1 as well. But in this box, we have energy 2. And in this box, we have, an even different energy. So I'm going to call that energy 3. And you kind of keep going, so on and so forth. And what you'll see is we're starting to develop the likelihood of seeing energy 1 and the likelihood of seeing energy 2, so on and so forth. Okay? So we do this for a really huge ensemble. Now I'm just going to truncate this a bit to kind of make the point of likelihoods. One more time, each and every one of these boxes has the same number of particles, right? The same volume, the same temperature. But let's say that I analyze this ensemble, which has 1, 2, 3, 4, 5, 6, 7, 8 different systems inside it. And I look at energy, right? And each one of these was set up identically, but different energies result. It looks like out of my 8 boxes, there's a 5/8 probability to see energy 1, right? We would call this the population, right, to see 1. Populations are probabilities. The probability in this ensemble to see energy 1 is 5 out of 8. The probability to see energy 2 looks like 2 out of 8. And the probability to see energy 3 looks like 1 out of 8. So now we can start to talk about likelihood of observed energies by setting up this ensemble. And we wouldn't just do it theoretically with 8. We would do it with so many that we were so sure that we could have a fractional probability that refers to the population of states inside your ensemble. How likely you are to see that particular energy, right? Now, if I can set this up Even though this is filled with a mole of particles and this is filled with a mole of particles, I don't need to know exactly what all those particles are doing, because I know whatever is going on for this fixed N, V, and T, all right? It doesn't really matter what each and every one is doing, even though I know that's there, right? That it's underneath everything. All I really need to know is, well, there's a 5/8 chance to see this particular energy that I'm labeling energy 1. And what if it's like 1 kilojoule per mole or something like that, right? So there's a 5/8 chance to see 1 kilojoule per mole. And there's a 2/8 chance to see, let's just say that's 2 kilojoules per mole, for example, right? These are labels, but like I said, you can kind of take it and then expand to actual numbers, probabilities to see certain particular energies, right? So this is the main idea behind statistical mechanics. We make an ensemble, it has certain things that are fixed, and then we can generate probabilities or likelihoods of seeing certain energies. Now let's relate this to what we know about quantum mechanics, right? And let's look at different types of motions that we looked at last semester. And we understand that there's also interactions. Energies come from motion and interactions, comes from kinetic energy and potential energy. But just to kind of drive this point home, it's kind of easy to think about motions. And let's just draw a big E here. Right? And let's just think about one of our systems inside our ensemble. Let's look at translational motion. So the first thing we started out with in quantum mechanics was looking at the particle in the box, 1, 2, 3 dimensions. It described the motion of particles. It turns out in the grand scheme of energies and available energies, and especially approaching like room temperature energies, okay? The spacing between translational states is really, really, really tight. It's really hard to see any sort of energy differences. Now, you might not have picked up on that when we actually looked at quantum mechanics, okay? But as soon as you sort of start to creep up to that classical correspondence limit, and it actually doesn't take too much temperature to get up there, okay? It almost looks like these guys are really close and jam-packed together, right? If we look at rotations, it's a bit different. For rotations, there's actually a little bit more spacing, okay? So when I look inside my ensemble, right, it depends on how much temperature there is, but it might not be able to climb up to too many more states. Sorry, it might not be able to climb up to the same number of states as translation. And I'm going to make that point sort of pictorially in a bit, right? But essentially, you can populate a lot more translational states compared to the number of states you could populate for rotations. And then when you go to vibrations, and we kind of remember drawing diagrams where we had vibrations, and then inside the vibrations there were a bunch of rotations, that means that the vibration gaps are even bigger. Okay? And we even made a point last semester to say, well, even at room temperature, vibrationally, most things are in the ground state. Okay? Electronically, we know that we make electronic transitions when we perturb a system and we throw some UV vis light in there. But at room temperature, just using like the thermal energy available, right? It's really hard to make those transitions. So those gaps are huge. Just realizing that this is how the world works is important. Translations, it's easy to make transitions between different states. Rotations is a bit harder, but you can still do it. Vibrations, right? Vibrations have a pretty big gap, and then the electronic gap is even bigger than that. How this relates to everything we were just talking about is a system in our ensemble has a certain thermal energy defined by the temperature. So let's say that the temperature only comes up to this energy value right here, right? The energy only gives us enough motion, right, to come up to this value, right? And again, we kind of reference that as a thermal energy. Well, then if I look here and I think about what each individual particle is doing, okay, it's translating all over the place. It's rotating a bit, but it's in its vibrational ground state and it's in its vibrational electronic state, okay? So thermal energy is what we focus in on for StatMech because we're trying to make the transition between quantum mechanics and thermodynamics. Thermal energy is like how far up these ladders you can come. Okay? Now, it's not definite. Like I said, if there's a certain thermal energy here, it could mean that most systems in our ensemble are in their vibrational ground state, but there might be a small population that go up here. Okay? But again, it's all about probabilities, all right? If this was really the thermal energy and there was that much space between the energy and where the next state was, there would be a very low likelihood to find a system up there, right? Most of the systems will be down here. Whereas for translations, okay, the systems are going to fill up a lot more states, right, than are filled for, say, vibrations or electronics states. Pretend that each one of these X's is a system in our ensemble. Okay? The thermal energy tells us how they populate these states. Now, how the states are populated translates directly into your observed energy. If I want to populate more states, what am I going to do? To populate more states, I'm going to raise the thermal energy. So a lot of our focus in StatMech is making these connections and then saying, well, what happens if I change the temperature? What's the effect on temperature in terms of what you see in terms of quantum numbers and quantum states? And I can think about probabilities and I can talk about likelihoods. And then from there, I can talk about, okay, all of these are particles in one of our boxes, or all of these are a system in our ensemble. What is the likelihood to observe a certain energy? What is the actual internal energy? The average value for energy. Okay? So it's not the easiest thing to grasp, but if you have this picture in your head, I think it definitely helps. Temperature kind of helps us move systems up these energy ladders, all right? It moves particles up these energy ladders, all right, to create a bigger observed energy, all right? But again, it's all done on average. So it turns out where if you do apply mathematics to this situation, and you think about developing probability distributions, and we kind of even showed how like a simple idea where we can kind of think about them as fractions and we can count them, that's not entirely useful, right? What you end up with in the canonical ensemble 4 are p sub j's. And try to make these like small p's because eventually we're going to reintroduce pressure and we're going to use big P. So make it like a small p, right? These are going to be our probabilities. So imagine, I just kind of laid out a way to analyze these thermally. Okay, these situations thermally. Imagine we carry that out mathematically. It turns out that these probabilities have a certain form. E to the minus beta E over Q. Okay? And we'll define symbols in a second. But essentially, remember how we got like 5/8 and 1/8? This is the way to mathematically actually get it correctly and accurately, okay, for our systems that we're looking at. Okay. Now, Q is incredibly important in StatMech, and most of the information is contained inside Q. Right? P sub j, think about that, is the probability to observe a certain energy state. Like a certain energy for the whole system. Like a certain, remember how we labeled them 1, 2, 3 before? What's the probability of seeing that particular energy? That particular energy has this certain value, right? And Q, which is known as the partition function, all right, is a sum of e to the minus beta e sub j's. So the probability to see that one energy is its own little e to the minus beta e sub j divided by a sum, right, of every e to the minus beta e sub j's for all possible energies that might be in that ensemble. Okay? Beta is 1 over kT. And there's where temperature plays a role. K is the same K from last semester. It's the Boltzmann constant. We'll make that a capital B. Or Boltzmann's constant. Okay? And this is all you really need to know to start to attack problems. Instead of coming up with a bunch of systems in ensemble and actually counting this out, it's really impractical even to do that. If we had the time to do the math, what you come up with is this magical expression where all I really need to know is the temperature, and then I know beta, and I need to know the set of energies you could possibly see, and then I know how to get my Q, because I just take a sum of all those, right? And then that's all you really need to throw into this formula to figure out what the probabilities are. Once you know these probabilities act in the same way they acted last semester. If I then want to talk about the average of something, like average energy, for instance, which is actually our internal energy. Remember how we did calculations like this before? We can sum up all of the probabilities that we're looking at times each individual energy. So as soon as you know Q, you know probabilities. And as soon as you know probabilities, we can use probabilities in the exact same way we did last semester to talk about sums of probability times the value you're trying to observe. Remember in quantum mechanics, we made this like an integral, but we don't have to do that right now statistically because we're going to say that these guys are quantized. So right now, this is going to be good enough. A sum of probability times outcome is going to give you your average. Average E, which we've been focusing on all semester, what are the energetics of this, is internal energy. So I'm actually going to cut off here. Things still might be fuzzy, okay? What we're going to do next time is actually apply math to this. And I think that's where things start to really rectify and really start to come into focus and get more clear. But still, all of this is worthwhile to try to wrap your head around as much as you can. It's all about thermal energy and thermal effects on ladders of energies. Getting probability distributions. And then once you know the probability distributions for a set of system energies that consider all the quantum states underneath, right? Once you know those probabilities, then you can start to talk about averages. Okay? All right, so we'll do that next time.